So we'll go ahead and define, what did I say, LST to be, there's your quote for you. LST is what? 1, 2, followed by the list 3, followed by the list 4, 5, like that. That's LST. So LST looks like this, and I want you to get the 4. All right? So, what does car do? Car gives me the first element of the list. What does could'er do? Yep. Returns the rest of the list as a list. Okay, so if I take the could'er of this list, what will I end up with? The list containing this. Correct? If I take the could'er of the could'er, what will I end up with? The list containing this. Right? So I want the could'er of the could'er. That gets me the list containing this stuff. What do I want from that list? One more could'er. Well, that's a 1 list I'm looking at right now. I have this list, the list containing just that 1 element. I want the car to give me that 1 element. So here, let me show you this. So I'm going to do the car of the could'er of LST, which will give me the list 3 followed by the list 4, 5. If I don't take the car of that, I'll have the list containing that 1 element. Make sense? Here's a list containing 1 element, which is a list. Make sense? All right. So the car of the could'er of this guy is going to give me that list as that element. So now I'm sitting looking at this guy right here. What's the car of that list? 3. What's the could'er of that list? The list 4, 5. So I want the could'er, right? So I want the could'er of that list. So that should give me the list 4, 5. And I want the car of that, which will give me the 4. So I want the car of this guy. Oh, car of the car. Gives me the 4. Because I have the could'er would be the list containing the 1 list 4, 5. This 1 element. So I had to take the car of that to give me that list, and then the car of that to give me the 4. Make sense? And let's see, are we able to do, then we say it only goes 4 deep. CAADADD of LST. No. Huh? Oh. All right, extra credit if you could pronounce that. The cadadder. No, the cadadder.
The cadaddy.
All right, that makes sense? What we did there? How many people got it? 0 people got this after warning you that there would be a quiz?
We never did anything like this.
We didn't do it.
Sure we did.
Not with
No,
multiple
it's
lists.
your definition inside of another.
Your definition.
The
could'er gets the second element.
Element.
Yeah,
Elements can be all sorts of things.
correct. But you didn't say that the could'er couldn't get the element within the element.
What?
So
Yeah.
to your
yeah.
definition,
No, I agree with yes.
you could get.
Can you give me an example of what my definition doesn't cover?
So by your definition,
Could'er would not give me what?
You would get the actual elements within the list. You wouldn't get the list. You would get the elements within the list.
All right, so you're saying that my definition of could'er would give you the list 2 out of this, not the list containing the list
Right.
1, 2.
Wait. Okay, yes, I see that that's the functionality, but based off of
I mean, the first element of that is the one element. So the car of this guy would be the list 1, 2. The cdr would be the empty list. So what's the real issue? What was our struggle here? The second I threw more lists in there, you chose not to treat the lists as elements. You chose to treat the lists as scary lists, right? And lists have cars and cdrs that could be applied to them. So apparently not enough 20s were
Or singles.
or singles. Maybe I shouldn't have thrown that single back. What? Go ahead.
So is the list just counted as one element?
Everything is an element. A list, it's a loosely typed language like we mentioned last time. A list is an element just like an A is an element, just like a 1 is an element. So this guy right here, this original list, I'll just type an LST down here. This is a list containing an element, and an element. There are 3 elements in that list. All right? So the car of the cdr, the cdr of this list is that guy, the cdr of that list is this guy, the car of the cdr is this internal list. The CADDR of LST is that internal list. The car of the cdr. Make sense? As an element. So this is no different than if I had said define LST2 to be 1, 2, 3. Except I need to actually write this as a list, right? So there's LST2, and then if I take this guy, the cdr of LST2, it will give me the third element, which is a 3. Just like it gave me the third element there, which happens to be a list. Go ahead.
What if you add another cdr to that? Or would that not work?
If I add another cdr to this guy, yeah, it would work. What would it give me? How many elements are in this list? Element 1 is this guy. Element 2 is this list. So the cdr of this guy, the CDADDR, would be the list 4, 5 as a list. So it would be the list containing the list 4, 5. So CDADDR, is that as deep as we can go, I think? Nope, that was not allowed either. So if I take the cdr of this guy, I get the list containing the list 4, 5. See, easy.
And then if you take the cutter,
Go ahead.
So for that one, if we wrote a CADDR,
For right now, let's operate under the policy of we just use cars and cdrs. That way we don't get too confused with the CADDR and all that stuff, because it's going to be limiting anyways. So for us, just for everybody's sanity, I'm going to rewrite this. This is the cdr of the car of the cdr of the cdr of LST. Okay? So we'll use this function. Okay, so what do you want me to do based off of this?
CADDR.
The who?
CA. So base car, cdr. 3 cdrs.
Okay, so of what? LST or of this guy? This guy right here. So you want me to take the car of the result here. So this is the result. So the car of this result is going to give me what? It's going to give me the list 4, 5. And what's the cdr of that going to give me? As a list. And what's the cdr of that? You said you wanted 2 cdrs?
Well, I was talking about that for the quiz.
What?
For the original? Yeah, the original.
Oh, like LST?
Yep.
All right, what do you want me to do? You want me to say the car of the cdr of the cdr of the cdr?
Yep.
That guy right there? Okay, well, before we press enter, let's see what it should do. So first of all, here's our list right here. The cooter of this list is the list, this guy, right? The cooter of that list is the list containing this list. What's the cooter of that list? Here's the entire element right here. What's the cooter of that list? The list containing the list 4, 5. So is that my third cooter? So first cooter is this guy. Second cooter is this guy as a list. As a list. So this is my second cooter, that guy in a list. What's the cooter of that? Not yet. The error doesn't happen yet. He wants the cooter of the cooter of the cooter of LST. So I'm asking you, what is the cooter of the cooter of cooter of LST? The empty list. Why is it the empty list? Well, let's look at what the cooter of the cooter is, just so we can see what we're dealing with there. Let me just steal this guy. It's the list containing a single element that is that list. What does car get us? The car gets us the first element of a list. The cooter gets us the rest of the list as a list. This is a list containing exactly one element. The element happens to be a list, but who cares? So I might as well be looking at the list containing a 3 right now. So what's the cooter of the list 3? The empty list. It's the rest of the list, not including the first element. That make sense? Go ahead.
So would the car of LST just be one in the list 1 and 2?
Car of LST would just be 1. Yeah, because here's LST. LST is a single list. First element is a 1. Second element is a 2. Third element is a list. That make sense? They're elements. List of elements. All right, so nobody got this right. I got everything but the right answer.
I still think
showed
the
a good
functionality.
progression through the list.
Pretty sure.
The functionality is fine now.
Pretty sure I explained cooter.
Your explanation of it yesterday, we didn't do any explanations with lists inside of lists. Like, we only did...
Yeah, we didn't have to.
Well, clearly we did, because no one got the quiz, which was on lists inside of lists.
Yeah, everybody overthought the quiz. We talked about elements.
Okay.
A list is nothing special. But we just know that cars and cooters operate on lists. We said that, right? We know that cars and cooters operate on lists, correct? And we did talk about lists inside of lists. We talked about Lambda last time, and we had the word Lambda followed by the opening parentheses, so we had a list in there, because then we have cats doing dogs, or dogs doing cats, or something like that. Yeah. Remember correctly? That was a list inside of a list.
We were really talking about lists.
we were talking about interspecies breeding at that point in time. So
We discovered how they came up with cat dog.
all right.
It was just a semi-poorly defined definition. We'll leave it
No,
that.
it was an accurately defined definition.
It was a perfectly defined definition.
Lists of elements.
Based.
It was
Okay,
like-
so
it was
the
like
inference
definition.
everyone
He never
made
said
from your
element couldn't
definition,
be a list.
because no one got it right, the assumption that everyone made from it was that you were not going to get a list, you were going to get the elements of the list.
Yeah.
With the cooter.
Yeah, no, I think...
But
That's the assumption.
Okay, so in this example, you're saying that if I took the cooter of something like this,
Yeah, we would get the elements.
you would get the
The two or
You would get the list. You would get You get a list of.
At a glance, you would think you would get a 2 out of that.
Yeah.
Yeah.
You would get the list containing a
Right.
2.
Yes.
So 1 less layer.
Right.
How much money you got on you?
Actually, a lot.
You don't want to know.
You don't tell me. Tell me the dollar.
$1.
I got 50 cents to my name.
I will take care of those drives for you and pay you for them.
All right, so
All get
shut up! While I'm considering whether I'm going to count that quiz, we're going to keep going. All right, so this part right here, deriving recursive programs. So now we're going to actually start writing programs. You guys couldn't even do cars and cutters. This is embarrassing. So in any case, we need to break, if you remember back to 200, we need to break our stuff down, our problems down into little tiny baby steps, okay? So the smaller subproblem principle. This idea, if we can reduce a problem to a smaller subproblem, we can call that procedure that solves the problem to solve the subproblem. So we're going to have a whole bunch of little helper functions. That's what that basically says. If we have to accomplish this, we need to break it down into little tiny steps. And we just saw us doing that. As we walked through this list here, I said, what will the cooter give us? What will the cooter of that give us? What will the cooter of that give us? What will the car of that give us? That kind of stuff. So we need to break it down into each individual step. Yeah.
David said he has exactly $69 for you.
That's true.
So why did his assistant need to deliver that information?
He wasn't going to say it.
All right.
He's Beyonce.
All right. So we're about to introduce another function we have access to. That way I can ask you even more difficult questions. Save this.
Also, when will the PowerPoint be up on Blackboard?
Well, I can put it up right after class. Shut up! I shouldn't have to say that more than twice. Shouldn't have to say it at all. All right, so we have our toolbox. Toolbox has define in it a car, a cooter, symbol, number, lambda, and now we're going to talk about lambdas more today. But now we're going to
add even because you used that one.
I don't know if there actually is a function for even. There might be. So in any case, length. Length gives us the length of a list. So for instance, the length of the list ABC would give us a 3. What would the length of LST give us? I'm pointing over to the board over there.
3. I got 3 elements.
It has 3 elements in it. So length LST gives us 3. The number of elements in the list LST. Make sense? All right, so that gives us the length of a list. So another standard scheme procedure that we have access to now. Okay, so let's get through some of this crap, blah, blah, blah. We need to get to the hard stuff. I'll give you access to this one, but I think you should use it with care. This is kind of a bypass thing for cars and cooters. So list ref kind of gets us the index of a list. So this saying get element 1 or bucket 1 from this list, which will give, this is bucket 0, this is bucket 1, this is bucket 2, so this will get me the B. Okay?
So we could not use list ref to get the 4 out of that, like by itself.
Not directly. Yeah. So what you could do here is we can say list ref LST2, which will give us that list, right? Okay. Then we could take the cooter of that. Well, actually, then we could take the list ref of 1. Then we could take the list ref of 0 if we really wanted to just stick with list refs. My feeling is that in most cases, you're better off dealing with cars and cooters. Every now and then, list refs might be convenient for dealing with like elements, like lists that have 2 elements in them, getting bucket 0, bucket 1. That could be, so that's the car versus the catter, the car of the cooter. But, you know, whatever kind of makes you happy, I guess. But we'll give you access to list ref. Okay. So list ref gives us the nth element of a list. Now, what we want to do is we want to understand how that's written. So if we were having to write a function called nth element that takes a list as a parameter as well as the element that you want, 0-based element, 0, 1, 2, whatever, okay? This is how we're going to do it. Now remind me, I'm going to actually switch back here to Scheme for a second. We're going to start writing some stuff up here, and then we'll flip back there. What's a lambda?
Unnamed function.
Yeah, it's an unnamed function. So typically in most languages, when we create a function, we give it a name, correct? In Scheme, it's like we associate it with a variable name. All right, so, and we do that with define. So we're going to say define, what do they call it, nth element, like that. So we're going to define nth element to be a lambda procedure. And this guy's going to take in 2 parameters. All right, we need a list, and we need which element in the list. So this guy's going to take in a list and a position in that list. So we have a parameter list for our lambda expression. Okay? Now we need to introduce how we do conditionals. Well, first of all, just so I don't have to flip back to the book, hopefully you guys, apparently somebody may or may not have shared the book with you on Slack, but I know nothing about it. So yeah, make sure that you have your Slack account because it could be beneficial in this particular case. In any case, we're dealing with how do we specify recursive solutions to problems. So if I give you the list, for example, let's just kind of go down here with it. I give you the list 1, 2, 3, and I want to get element 2 from that list, which would be the 3. How would you go about doing that? Well, certainly we're going to use cars and cutters. Using the tools that are currently in our toolbox, walk me through, don't worry about the scheme solution. Walk me through the recursive solution to getting the 3, extracting the 3 out of this list, knowing that the 3 lives at bucket 2. This is bucket 0, this is bucket 1, this is bucket 2.
If n is greater than 0, take the cutter of the list and then subtract 1 from n.
Okay, so this is n. Is n greater than 0? It is. So what he wants to do is he wants to call this dude again with the cutter and subtract 1 from n. Is n greater than 0? It is. He wants to call this dude again, passing it the cutter and subtracting 1 from n. Is n greater than 0? It's not. So what do? Take the car. We return the car. Which is going to give us the 3. Make sense? So that's our logic that we want to write here. So now we need to see how we do, just like last time. Oh, well, just like how I've introduced any programming language. Languages have facilities for 3 things. Variables, we do that through defines. Now we need to be able to ask some questions. Okay? So, it's a functional language. So we have a function called if. And if takes a single parameter. Let's actually give you this guy here. So let's just throw if statement. Keynote is having some breathing difficulties. All right, so if we have if Boolean expression, true statement, false statement. All right, so the if function takes in 3 parameters. Parameter number 1 is a Boolean expression. What's a Boolean expression? Any expression that boils down to a single value, true or false. So that's the first parameter. Second parameter is the statement that we should execute in the event that this Boolean expression boils down to true. Third parameter is the statement we should execute in the event that this Boolean expression boils down to false. Make sense? All right. So if we incorporate that into our program here, we're going to say if greater than n0. If n is greater than 0, so this is the greater than function, and there's also a less than or equal to. Go ahead.
We have to check if the list is not equal to 0 too, or greater than 0.
We can have error messages if we want. For right now, let's keep it more functional than too much error checking. So if n is greater than 0, what are we supposed to do? And do what with it?
Pass it to the function.
Call the function recursively. So we're going to call nth element on the cdr of lists, passing it 1 minus n. So we're going to create a list of some functions here now that we have access to. So let's see, where's our toolbox? Continued. More tools. We have if. We have less than or equal to, greater than or equal to, equal to. Now for right now, dealing with numbers, that's all you need to know. But I'll give you a little foreshadowing. There's actually multiple versions of comparing things. As we get into this, it goes all the way from comparing things at the, at some point I'm going to refer to it as bone structure. But the punchline here is, think of it as kind of like how we compare pointers. Do both of these things point to the same place versus do both of these things resolve to the same value? But then we have actually a couple of steps in between. We have something called EQ, something called EQ question mark, and then something called EQV for equivalence. Then we actually have something called equals. Equals is the bone structure one. Okay, but that doesn't exist in your world right now. This is what exists.
What about not equal?
Not equal is this guy. It would be the not function. So to do not equal, you would do not equal. All right. We have our if. What else did I throw in there? Minus. So we have minus, plus, times, divide for all those.
Does it support modules?
It does. I think the function is just mod. So here, I'll give it to you just in case. All right. In case one of the homework assignments has it in it, and you guys can't come back and yell, "Oh, you didn't teach me that." All right. So if n is greater than 0, we're going to call our function nth element on the cdr of our list. So that's going to be our first parameter. That's going to be passed in as LST, along with whatever n minus 1 is. Okay? That's what we're going to do. That's our true statement in the event that this Boolean expression is true. What's our false statement? If that Boolean expression is false, what do we do? The result is car of LST. Don't have to return it. Everything boils down to a value. This function is going to boil down to a value. So all we do is say car. Go ahead.
Is it LST or is it nth element? Because we're finding nth element each time.
No, LST. This is the list.
Oh, okay. Oh, yeah, 'cause it's one.
So that's nth element. And if we want to call it, we can say nth element of, let's do 1, 2, 3, say give me the 2. I'll go ahead and run this. And there's our 3. But I can then call that again if I want element 1, 2, 3, and say, give me the 1. That'll give me the 2. So this is how we can write a function. So this guy right here is listref. So had I not shown you listref, you could have written listref yourself. Something that takes in a list as well as the index in the list that you want to return. All right. And here's that check that they did for whether the list is empty. And this is using that stupid racket language thing, the report list too short exception. Go ahead.
That isn't actually list ref though, is it? Because if you were to, like, using our example, if you started taking, like, the cutter and the cutter and the cutter, you would start going into the other lists, whereas with list ref you would not, correct?
No.
So if I were to take that one, if we were to do that, it would not go into the other list. So it would not.
You want to say something like that?
Sure.
The second element should be the list 3.
Yeah.
Because this is just an element. So if I say list 3, 4 there, second element's going to be the list 3, 4. And if I say third element, we're going to have problems. It'll probably give me the empty list. All right, so little example of using a lambda, a named function, associating it with a name. So this is where we give the function a name, and then actually calling it using some examples. All right, anywhere in the book when you see things like this is EOPL, that's Essentials of Programming Languages. That's the book's built-in language error checking crap. We don't use that. So pretend like that doesn't exist. Okay. Forget about that. All right, so let's practice a couple other things. Let's look at remove first. So procedure remove first should take 2 arguments, a symbol, S, and a list of symbols. It should return a list with the same elements arranged in the same order as list of symbols, except that the first occurrence of the symbol S is removed. So remove first. We'll leave nth element up there so you have something to reference for just some of the syntax. So we want to define remove first. We're just practicing here. To be a lambda. And this guy should take in 2 elements. It should take in a symbol, and it should take in a list of symbols. All right? And what we want to do is we want this function to boil down to whatever LOS is, whatever list of symbols starts off as, with only the first occurrence of S removed from it. So for example, if I have, if I say A is S, and A, B, C, A is LOS, the result here should be the list B, C, A. Well, in this particular case, it would be, because the very first element is A. Okay, but if I had said here, so we'll if I said C, for instance, we would keep the A, we would keep the B, we would dump the C. Yeah, only the first occurrence. So remove the first occurrence of a symbol from a list, resulting in the new list. Make sense the problem we're solving? Okay, so let's use C as our example here. How do we go through this? We are going to keep looking at this list until what happens? Okay?
to the length.
We do have access to length. You don't have access to something else you're going to need to have access to, though. But you can tell me what it is here in a second. We can stumble upon something we don't know how to do right now. But then I'll teach you how to do it.
Whatever the value is at that.
Well, I need to, so generally speaking, what am I doing? I'm searching this list for the first occurrence of this guy, correct? And I need to keep searching this list until what happens? Or I ran out of list, right? So as long as this guy is not null, so let's go ahead and add another predicate to our, we mentioned it already, but we'll, so we have a predicate called null. That returns true if a list is empty, false otherwise. Okay? True if a list is empty, false otherwise. And I'll go ahead and throw in the other thing that, well, no, I want you to stumble on it. Okay, so is this the empty list? It's not. So I definitely need, I have some stuff to look at. So we're going to look at the car. Is this element the element I'm looking to remove? It's not. So that means I'm going to keep this element, right? So I'm going to be building a brand new list. How do I build lists? Up to this point, we've defined variables. Okay? I just want to build a list. I don't need to store it somewhere to use later on. I just want to ultimately boil down to a list I'm building. We have something called cons. Cons is a function that takes an element and a list and returns a new list with that element as the first element. For example, if I cons A onto the list B, if I cons A onto the list B, oh my gosh, cons I get the list AB. So the second element must be a list. First element must be an element. Could be a list. Could be a list. For instance, what would I get if I said cons the list A onto the list B?
The list with the first element, the list only containing it.
The list. The list whose first element is a list A. That element became the first element. Make sense? All right, so cons lets us construct lists. Now, one thing you'll see, in case you make a mistake like this, you can cons A onto B. Yells the second argument must be a list. Must be a list. Okay? So cons is how we build up lists. So now, going back up to this guy, I need to build a list. Go ahead, Doc.
So cons only takes 2 parameters. Like you can't do like 3 or 4.
You can do cons onto a cons onto a cons onto a cons. So I can say cons A onto the cons of B onto the cons of C onto the empty list. Okay. But I'll be nice and I'll say you can also do this. List A, B, C. Oh. Oh my God. I need an old priest and a young priest.
And large bottle of wine.
There's the list ABC. So you can use that as well. But usually we want to use cons, not because cons is better, but cons is very, very, very compatible with recursively specified data, as we're going to see here in a second. List will help us build a list when we know all the elements right off the bat. Make sense? Okay, so if I know I want to put A, B, and C in a list, I could just use list to put A, B, and C in a list. But if I want to create a list of an element followed by whatever's returned by a function that I'm going to call here in a second, probably a recursive call to a function, cons is going to be what we want. All right, so up here, again, we're removing the first element. We're removing the first occurrence of S in LOS. So I'm looking for a C. Is this the empty list? No. Is the car, so if it's not the empty list, that means it does have a car, correct? The car of the list exists if it's not an empty list. So given that, does the car of this list, does it match S? Does not. So A and C, not the same thing. So what do I want to do with A then, in terms of my final result? A is going to be part of my final result, right? So I'm going to cons A onto remove first of what? The cdr, passing it the same symbol, right? So I'm going to call this guy again. And now I'm looking at that. And what am I going to do here? I'm going to cons B onto the cdr. So I'll call this guy again. Is this the empty list? No. Is the car of this list match S? Yes, it does. So what do I do? Do I cons? No. How do I skip ahead? Just take the cdr. Just take the cdr. So we'll ask the question, if null LOS, I'll return the empty list. If I ran out of crap to look for, boil down to the empty list, because we know that at the end of the road, cons requires an empty list, right? Otherwise, it screams us and says cons doesn't work on things when the second parameter is not a list. So if we finally ran out of stuff to look at, we'll go ahead and return the empty list. But notice we don't use the return statement. Everything is a first-class object inside of Scheme. This function would just boil down, this version of the function, this call to remove first, would boil down to the empty list, which would then probably string along with previous calls you had to it. All right, so if we're out of lists to look at, return the empty list. Otherwise, we want to ask a question. If the car of our list is equal to S. If we're looking at the same thing, the car of the list is equal to S, what do we want to do? Cons who?
The car.
No, it's the cdr.
If they're equal, we're removing it,
Oh, that's, yeah.
right? So we're just going to return the cdr of LOS. Otherwise, is where we do the cons. Otherwise, if the first element is not the same as our symbol, we're going to cons the car of LOS onto what? Onto remove first of S and the cdr of LOS. So we move first. We'll say C from the list A, B, C, D. Go ahead and run this. Oh, so here I have to introduce the new version of equal anyways. Equal sign is for numerics only. Remember I mentioned a few minutes ago that we have multiple versions of equals? The one we have to use here, well, the one we're allowed to use here, is it just EQ or is it EQ question mark? I think it's EQ question mark. There we go. So EQ question mark, I don't think EQ is a thing. It's not. So EQ question mark is how we compare symbols. Equal sign is how we compare numbers. EQ question mark is how we compare symbols. Then we have something called EQV, which is going to how we compare, not really lists. We'll talk about that.
Does EQ question mark only work for symbols, or would it also work for numbers?
I think it also works for numbers. Yeah. So if I say EQ question mark 1, 1, it'll give me a true. Yeah. So then you might say, well, why don't I always use EQ question mark? You know, there could be some truth to that. All right. Make sense for remove first? So follow this. This is just defining a variable. This is our unnamed function, takes 2 parameters, a symbol and a list of symbols. As long as our list of symbols is not empty, well, if it is empty, if I'm out of symbols, we're going to finish off our recursive cons with the empty list, since cons ultimately requires a list of symbols as a parameter. Or, I'm sorry, since cons ultimately requires a list as a second parameter, this fulfills that ultimate requirement when we finally end our recursion. All right? Otherwise, if it's not null, that means at the very least I have a car. There's a car associated with the list. So I'll see if that car is the same as the S, same as the symbol I'm looking for. If it is, that's the one I'm going to remove. So I'll go ahead and return the cooter of LOS. And that's the end of my cons. And that's okay because the cooter always returns what? 100% of the time, what kind of animal does the cooter return? A list. 100% of the time, cooter always returns a list. Therefore, if cons requires a list as your second parameter, I'm guaranteeing that at the end of the day, I'm either giving it the empty list to finish things off, or as soon as they find the dude I want to get rid of, I'm giving it the list that's the rest of LOS. Whatever's in there, but as a list. Otherwise, if it's not the dude I was looking for, I'm constructing a list here. And that list is going to be built of whatever's the first element of the list right now, followed by whatever's returned by remove first, passing it the exact same symbol, and everything but the car of the list. Make sense? What if I wanted to change this to be remove all instead of remove first? So I don't want to just remove the first time S is found. I want to remove S every single time it's found and only keep the non-S's.
Within remove all, would you just be using remove first? So you do cooter and then remove first again?
This guy here?
Would you, yeah, can you just do it recursively?
Okay. So you want it when we found a copy, we found something that was equal, we're going to remove it, but we're not just going to send it the rest of the list. What are we going to do?
Remove first the rest of the list.
Remove first the rest of the list. Like that. So if I found a match, we're going to call remove first on the rest of the list. But we need to do this as two separate functions, right? We have a remove all, and then we have a remove first. Well, can we do it as one? Think about our output here.
Let's get rid of that line. Remove first list.
If I say this, let's kind of walk through it. And let's say I'm removing the A. So if I'm removing all, so here I'll just type all here just so we're mentally we're all here. Okay, so A, I'm going to go through this guy. I found a match here, so what am I going to do? I'm going to call remove first on the rest of this list. Which will give me the B, C, A, D when I call it. Then I find the B. What am I going to do when I get the B? I'm going to cons the B onto remove first of the rest of the list. Then I'm going to get the C. What am I going to do? I'm going to con C onto the rest of the list. Then I'm going to get the A. Well, that's going to fail. So what do I do when I see the A? I'm going to call remove first on the cdr. Well, now we have a problem. This call was calling remove first on the cdr, right here. So I got rid of the A, I kept the B, I kept the C, found the A. What do I do in that case? I remove first on everything after the A. So ultimately this is going to boil down to the list D. When it turns into the list D, what will that ultimately become? That will ultimately become the result of calling remove first here.
But you don't have to put the location. Oh, okay. Never mind.
So if I rename this remove first, BCD. So now remove first actually does a remove all. Makes sense how that works? So just a little change, but now we're making two separate recursive calls. Another thing I'll throw out there, I mentioned it last time as well, but sometimes the book uses this syntax of a symbol followed by a dot followed by a list of symbols. I always treat everything just as straight lists. So when you write your solution, even though they might show the solution as being like this, they call them pairs, treat it as a list. It's a symbol followed by 0 or more symbols in this particular case, no dots. Love this one. Occurs free. So this gets back to our idea of, this starts kind of stumbling into languages, okay? So we go back and we look at lambdas a little bit more. Right here. Lambda is an unnamed function, and we're going to say version 1 of our lambda calculus expression in our miniature language that we're kind of writing an interpreter for right now, let's say, is going to be a list containing the word lambda followed by a list containing exactly 1. No more, no less. Exactly 1 parameter. Followed by a body, where the body can either be a literal or the body can be another lambda calculus expression. Okay, so those are our two elements that make up our list right now. So we'll say where body is a literal. What's a literal? What? Number or symbol, right? So A or 5, those are literals. Okay, so where body is a literal or a lambda calculus expression. All right, so this is our simplified version of our lambda calculus expressions for our initial thinking through our language. All right, And the thing that they want us to explore right now is this idea of something called occurs free. All right? And this has to do with variable scope. What's variable scope? When I say variable scope, what am I talking about?
How far outside of a function, or where in the program the variable is defined, and then if you're able to reach that. So if you go outside of the scope, you're not able to access it.
Where it's accessible.
Yes.
Okay. The variable scope deals with where exactly a specific variable is accessible based on where it's defined. Yep. So between the two of us, we got it all kind of spit out there. But that's what scope is. Scope is we define the variable someplace. In this case, we have one place that we can define variables. That one place a variable can be defined right now is right there. Okay? So in our simplified lambda calculus expressions for our little miniature interpreter we're starting to write here, there's only one possible place that a variable can be defined, and that is right here. And if a variable is defined right here, where would its scope be? The body here within that function. Okay? So think of this like a method, and here's the parameter to that method in Java. So anywhere inside of that method, we would have access to that parameter. Okay? That makes sense? So I'm going to copy this here real quick. But again, for us, in order to write occurs free, the first version of this, we only take parameter lists containing exactly one element. We don't allow 0 variables to be defined, so we don't allow no parameter functions, and we don't allow functions to have more than one parameter. All of our functions have one parameter for version 1 of occurs free. Okay? So let me give you some examples here. So occurs free deals with variable scope. As an example, we would say that in this particular case, y occurs free. Because y occurs, first of all, and it is not bound by the variable definition x. Therefore, y occurs in an environment where it was never defined. So we say that y occurs free. Make sense? Let's make this a little bit more complex. In this particular case, we would say B occurs free. Here we would say nothing occurs free. Make sense? What occurs free means? So here's some examples. What's a lambda calculus expression? By this definition, we go all the way back up here to our grammar for lambda calculus. That we talked about last class, right? Right here. Lambda calculus expression. It's either a identifier, so like 5, like C, something like that, or here's our second, what's this guy called? What's one line of a grammar called? What's a predicate? Function that returns a Boolean. So what's one line of a grammar called? What would our excuse have been if I had made that the quiz? It's a production. It's a production. Okay? The third production is it's a list containing two lambda calculus expressions. Make sense? So those are the possible animals that can exist in our lambda calculus expressions here. All right. So remember that for the moment. Go back down here to occurs free. So for instance, if this is my lambda calculus expression and we call occurs free, it's going to give us the element that occurs free in there. Well, no, we're asking, does x occur free in this lambda calculus expression? And the answer is yes, it does. Why? Because x is never defined. Therefore, the fact that it occurs means that it occurs free. Because variables are only defined in the second production of our lambda calculus expressions inside the parameter list. That's where they're defined. And because I don't have one of those animals here, it doesn't exist for me, right? Similarly, does y occur free? No. Not only do we not have any variable definitions, y doesn't actually occur in this lambda calculus expression. Doesn't even occur. Forget about occurs free or occurs bound. It doesn't occur. Okay? Occurs free x in this, so it looks like it's the other way around, the parameter list. So this is the lambda calculus expression. This is the lambda calculus expression. This is the variable we're looking for. So now we're asking, does x occur free in this lambda calculus expression? Well, first of all, does x occur? Yes, it does. X occurs right here. Does it occur free? No, because it occurs within the variable scope that is defined by this guy right here. So it's false. X does not occur free in the body. So the only place that a variable can occur is in the body of a lambda calculus expression, where the body could be an identifier, could be another lambda calculus expression, or could be a list of two lambda calculus expressions. All right, so in this case, x does occur, but it actually in this case occurs bound. So it's false that x occurs free. What about x in this one? Does x occur free in this lambda calculus expression? Well, we start off by asking, does x occur? Yes, it does. It occurs right here. And we only have one variable definition, which is y. So x occurs, and it occurs in a scope that does not have a definition of x. So it's true that x occurs free. So we get our true. What about this guy right here? This one gets a little bit more challenging.
Is it true because in the second list it occurs free?
Okay. So first of all, we have to decide, does x occur? X occurs actually in two separate places here, right? So we have, which production is this guy of our lambda calculus expressions? Production 1, production 2, or production 3? The third one, the one that's a list of two lambda calculus expressions. The first lambda calculus expression is this guy right here. The second lambda calculus expression is this guy right here. Now, in our first lambda calculus expression, does x occur? It does. Does it occur free? No, because it's bound right here. Doesn't occur free there. But we still have time. We have another chance. It's a bonus roll. Okay? So we have our second lambda calculus expression. And our second lambda calculus expression fulfills which production of our lambda calculus expressions? Production 1, production 2, or production 3? Production 3. A list containing two lambda calculus expressions. Here's the first. Here's the second. Okay? This guy is which production? Production 1. This guy is which production? Production 1. So this is a list containing two lambda calculus expressions. The first one is an identifier. The second one is an identifier. Does x occur inside of this lambda calculus expression? Yes, it does. Is it bound? It's not, because there's nothing binding over there. Make sense? All right. So x does occur free. Technically, it occurs both bound and free in this example, but all we're doing is we're asking a question, does x occur free anywhere inside of the lambda calculus expression that follows? Okay? Last one here. Occurs free x. Which production is this? 1, 2, or 3? 2. This is our de facto function version of lambda calculus expression. That's a list starting with lambda, having a single binding moment. This is the only place where variables can be bound. Okay? Followed by a body. Here's the body. There. Which production is that? Production 2. Okay? So we have another binding here. Z. So we actually have 2 variables being bound. We have a variable y and a variable z, both being bound. We don't know if they occur yet, but they're being bound. All right? So then we get to the body of that second guy right here. Which production is this? Production 3. The list containing 2 lambda calculus expressions. So here's the first element. We have x. Does x occur? Yes, it does. Does it occur free? Yes, it does. Do we even need to check the rest? No, we don't, because we can immediately return true for occurs free. But we'll go ahead and check the rest. Okay, but at the very least, x occurs free right here. Okay? Then we have the second element of that guy. Which production is this? Production 3, which is a list containing 2 lambda calculus expressions. In this particular case, it's production 1 and production 1. Does x occur here? Nope. Does x occur here? Nope. So x does not occur free there, but x does occur free in the whole thing because it occurred free right there. It occurred there and was not bound. Make sense? Okay. Oh, now I see that it actually gave us the... why did I scroll all the way up top? All right. So next time what we're going to do is we're actually going to come back and write occurs free. They give us an implementation down here, but we're not going to look at it. We're going to write our own. But there is a homework assignment already up. The homework assignment is to do questions, starting on page 26, I think. Starting on page 26 here. Questions 1.15 through 1.20. So 5 questions. So for instance, this one, duple takes n and x, returning a list containing n copies of x. So if you duple 2 and 3, you get a list of 2 3s. That kind of stuff. So little drill type stuff like that. The 1-star ones are hard. The 2-star ones are impossible. Okay, so 1.19 are 1.19 is impossible. 1.20 is a single star. We'll do a 3-star one at some point, which actually is just punishment. All right. Questions, comments, concerns, bribes.
We need to bribe maintenance to turn on these.
All right. I will see everybody on Tuesday.